I think it had been recording. It's fine. Word. All right. Throw them up. Forward. Yeah. Any zeros?
I was thinking I did something short of zero. That's okay. We'll see. Oh yeah.
Which one did you do? The first one?
I think both.
Luckily,
Yeah. Yeah, I know. I'm counting.
So maybe you're counting on the first one. And maybe you're counting on the second one. Whoa, I thought the second one was easy.
Yeah. That's why I raised my hand.
I think I used to use it sometimes.
Hopefully, yeah. Oh, I didn't even say that. Yeah. All right.
I'm depending on all my points for the third.
So,
All of my points. If I
all right.
not.
Wait a minute. Where'd my notes go? This one go?
The thing is, I got it.
My notes are all out of order. I can't teach when my notes are out of order.
That's it. Class.
Okay, here we go. Before I get started, are there any outstanding questions, comments, curse words? Okay. So now today is going to kind of end our sort of rephrasing of much of what you have seen in special relativity before. So today I'm going to touch on a lot of classic things that you see in special relativity, albeit working mostly and largely motivated by our newer way of thinking about things. And then starting next time, we're really going to start digging into ideas which most of you have probably not wrestled with so much. Okay. So what we're going to talk about today is essentially the tensorification of kinematics and dynamics. And if you want to figure out if that's a word or not, just go look it up on online at about 6:45 after I've had a chance to enter it into Wikipedia. Or the Oxford English Dictionary, which I have unique access to. No, I'm just kidding. Okay, but we're going to tensorify kinematics and dynamics. Now what I mean by tensorify is you're all very familiar with kinematics and dynamics from as early as Physics 1 or perhaps the womb, wherever, I don't know. But you're well aware that the kinematics and dynamics that you started working with was in terms of three-dimensional quantities, okay? Those things are generally not going to be good tensors in space-time. So our main motivation for today is to get the language of kinematics and dynamics into full tensor expressions. And in doing so, we're going to discover much of the joy of special relativity, because after all, once you've got things written down as space-time tensors, it's automatically relativistically invariant. So let's start with sort of a survey of some of the important three-dimensional quantities that you've worked with in kinematics and dynamics. So you know that in kinematics, you sort of start off with this idea of the position as a function of time, where usually you work in 2 or 3 dimensions. So this x might be x1, x2, x3, or just x1 and x2. Again, I'm going to stay away from calling things x, y, and z because this way I can index them by a number. But the basic quantity that you were thinking about was, I've got some object and it's moving, and I would like to know its position as a function of time. And of course, I coordinatize the space, and so I provide each coordinate position as a function of time. And then once you've got that on the table, you can take the derivative of it to obtain the components of the velocity with respect to time, where of course that derivative is defined as a derivative with respect to time. And then from that, you can take another derivative, if you so choose, to obtain the components of the acceleration as a function of time. Okay. And then, from the early days, you saw that the acceleration played also an important role in the dynamics through Newton's second law, and then that can be rephrased in other ways depending on what kind of mechanics you're doing. But in the earliest setting, you might write down Newton's second law. So if I've got some object B, then the mass of that object times its acceleration is provided by the sum of the forces acting on that system. And then if we actually do this in a component form so that we can kind of steal the notation we're already using, we might do this, which I can leave the j's in there. So the sum of the forces in the ith direction is the mass times the ith component of the acceleration. And then at some point later on, you realize that this could also be written as the time derivative of the ith component of the momentum. Okay? Where the linear momentum here is defined as the mass times the ith component of the velocity. Okay? This should all be, yes, Gabriel.
The B's like,
It's just an index labeling that there's some object.
okay.
So I'm doing Phys 1. We can totally like ignore B and just say, I've just got something and it's got an acceleration. Yeah. I kind of like, I just came from studio, you know, so I'm trying to be like, got my indices right. And, you know, this is a force, it needs two indices. I want you to know. Okay, anyway, all right. We will not let Phys 1 students see these lectures on YouTube. I'm going to block them. Anyway, okay. So in all of this, of course, in principle, I takes the values 1, 2, and 3. Okay? So if we want to do special relativity, if we want to move this story up to 4 dimensions, we know that at least one of these gets generalized in a very natural way. So xi, the position of something, or the 3 coordinates telling you the spatial position of something, get appropriately replaced by the set x mu, where mu takes values 0, 1, 2, 3. So in the 4-dimensional language, we talk not about the spatial position of something, but its position in space and time. Okay? And so we might expect that there should simply be some sort of 4-dimensional generalization of velocity, which I'm just going to call u. And since it's a 4-dimensional vector, we anticipate it's a vector since v itself is a vector in 3 dimensions. I'm going to give it a space-time vector index mu. Okay? Now, this is kind of what you might naively expect, but you immediately run into 2 problems. Okay? 2 problems. What the hell is U0? Okay? So if you notice, when we went from the 3-dimensional spatial positions to the position in space-time, the 1, 2, 3 values of this are just these. Like all you're doing is literally adding on a time piece. Okay? So you can imagine when you go from our usual velocity in 3 dimensions to the 4 velocity, that the 3 spatial components of this become the 3 spatial components of this, but then what is the time-like component of this? What's the U0 term? I don't know. It's not obvious. It's obvious here. The 0 component is just your position in time. But what is this? I don't know. Okay? But there's a second, more significant problem. If we try what we might naively guess, and that is to define the 4 velocity, I was going to say something else and then I changed my mind, that's why it sounded so weird, to be the derivative of the position with respect to time. That's a natural guess, right? Following the analogy with what we did in 3 spatial dimensions. We discover a problem. Okay? What kind of quantity is dx mu, Adria, in the scheme of tensors versus not tensors, vectors, scalars? Give it a name. What is dx mu?
Yeah. A dual vector? We called it like a kind of dual vector last time.
Well, it's got an upper index. What kinds of quantities do we encounter with upper indices?
Okay. Is it a vector?
It's a vector. It's the components of a vector. Okay? We talked about the infinitesimal displacement vector and said that has components, dx mu, and then there's some basis set of dual, or a basis set of vectors. But The one thing that we know is that this thing right here, this numerator, is a vector in space-time. Okay? Next bit. Chase. What is that? DT.
It's a scale.
That's a good guess. Wrong, but it's a good guess. Actually, we wish it was a scalar, but it's not.
Is that also technically a vector?
Does it have an index?
No.
Probably not a vector. What is that thing? That funny little thing? That DT thing? What do you think? What do you take? Say again?
It's like an operator?
Ooh. Have you taken some quantum mechanics courses or something?
No.
Operator. No, it's not an operator. I mean, if we promoted it to an operator, yeah, no, it's not. What do you think DT is? What would DT be? It isn't an infinitesimal.
Like a coordinate differential, right?
It is a coordinate differential.
Is it invariant?
It's not invariant.
Dual vector.
It's not a dual vector. Let's throw out every single word. I'll give you a hint. DT appears in something that I've already written on the board. What does DT appear in?
All that number.
Well, it appears there because I wrote it on the board.
No, also up there.
It does appear up here, but let's stay away from that language for a moment.
dx0?
dx0, which is what?
A vector.
So what he's saying is, if you think about this vector, the zero component of it is just dt, or it's c dt, but it's dt. So what is that quantity?
A basis vector?
Nope.
A component of.
It is a component of a vector. That is exactly what it is. This is one component of a vector. Now, you might laugh, but this is incredibly important to understand. If I take a true vector, which transforms as a vector should transform, and I divide it by a component of a vector, which, by the way, has a specific transformation law, but it's not a vector transformation. It transforms like a component of a vector. If I take a vector and divide it by this, what is the resulting object? I don't know, but it sure as hell ain't a vector. Okay? I mean, you know how a vector transforms. This transformation law is what dx mu does. It's what you want u mu to do. But if dx mu transforms like this, and then dt transforms in some wonky way, there's no way that dividing them is going to give you the right transformation rule. Okay? Then this thing is not a vector. Which of course means it's not a tensor at all, because it sure as hell ain't a scalar. It does transform, the components transform. It's not a second-rank tensor. Okay, so the problem is, and yes, Chase, your original guess would have been like wonderful if this had been a scalar, because if this had been a scalar, then dividing a vector by a scalar would give us a vector, and all would be cool. Okay, but unfortunately, just trying to divide by time isn't going to cut it. We need something more sophisticated. Okay, so what are we going to use? Well, to figure out how we're going to get around this, let's think for a moment about why dt works in three-dimensional kinematics, so that we can sort of get an inspired guess for what we might replace dt with in four-dimensional kinematics. So in three-dimensional kinematics, what we have in mind is that you have your spatial directions, and then there is some universally agreed upon time. It's some quantity that you can parameterize things with. Parameterizing just means that things depend on it. This is universal. It's monotonically increasing. And hell, it's invariant. Okay? It's a wonderful thing. Everybody agrees on the time that, I died. Time only gets larger. It's invariant. Time doesn't care whether you're moving, sitting still. Okay. Now, of course, you can immediately see the problem in relativity, right? In relativity, time is transformed between different reference frames. Okay? So time is not an invariant, and time is not universal. Okay? So what we would like is, in the context of four-dimensional space-time and relativity, to identify something that has these properties, even though it might not be time. Okay? It's going to lead us to a choice which is a little weird. It's going to give us some sort of counterintuitive results. Okay? But fortunately, it does reduce to the standard definition if you take the non-relativistic line. All right, so without any further ado, here we go. So if we think about something that is moving through space-time, and I will only draw two spatial and the time-like axis, because I can't draw four-dimensional that well. But if we think about something that maybe starts at the origin and then moves through space-time, then, and bear in mind the quantity that the object that I'm thinking about in this case is like a point. It's like, an electron or something. So this thing moves through space-time, but in space-time, that motion creates what we call a world mind. Okay? If you look at an electron in space, at an instant of time, it's just a point. But if you could look at it in space-time, that point will trace out a line. We call that the world line of the particle. Okay? Now, here is the trick. Based on that one simple little picture, can you identify a monotonically increasing quantity? That is something which only gets larger, never gets smaller. Say it again?
CG.
Yes, CT, but CT is not going to be useful to us because it's not invariant, it's not universal. Other quantities, yeah.
The invariant, like the distance from where it starts, the same invariant we've used before.
Well, I'm going to connect it to that. Yeah, go ahead.
Space-time interval?
So you guys are saying the right thing, but I'm just going to say it in a more mundane way. The length of the line. Literally, the length of the line is always increasing. Right? Because it starts out with zero length, and then as it moves through space-time, the length of that thing grows. Okay? Now, if we actually write down what the length of that line is, what we'll find is that it is expressible in terms of an invariant that is agreed upon by all observers. It's universal. Okay? Now, as a first guess, we might say that the length would be given by the integral of the square root of ds squared. Okay? Now that looks a little busy, but that's secretly just code for integral ds. Okay? Okay, you have to integrate it because, ds is a set of coordinate differentials. And unless you're moving on a straight line trajectory, you actually have to integrate over it because your actual displacement along the different coordinates is not necessarily linear. Okay? But there's a problem with using that definition. Can anyone identify the problem with that definition? Well, let me write down ds squared for you. So that's our expression for ds squared. I want you to look at this expression for a moment And I want you to tell me, what is the sign, SIGN, of ds squared for something that is moving less than the speed of light?
Should be positive.
Well, I'll give you a really, really simple case. Let's think about something which is at rest. If something is at rest, what are the values of dx, dy, and dz?
0.
They're 0 because you're not moving. What is the value of dt? It's just some quantity, like it's a time interval, okay? So if something is at rest, what is the sign of ds squared? It's negative. Okay. So we see a problem, right? We're taking the square root of a negative quantity. We don't want to do that. Okay? So what we're going to do is we are going to slightly modify this and call this the magnitude of ds squared. Okay? And then taking the square root makes sense. All right? But we're going to avoid calling this the integral of ds because, what do I mean by ds in this context? Is ds positive or negative? So we can just leave it expressed like that. All right? Now we're going to give this thing a name. We're going to call it tau. And that's just adopting the convention in the literature. And we are going to use tau as the parameter to define velocity. Okay? All right. So here we go. Xi of t, that is our conventional three-dimensional spatial velocity, is going to be replaced by x mu parametrized not by t, but now by tau. Now notice the symmetry of what I'm doing. In 3 dimensions, I used a monotonically increasing invariant to parameterize the path. In 4 dimensions, I'm using a monotonically increasing invariant to parameterize the path. So I'm doing the same thing in spirit, even though the quantity that I'm parameterizing with is just a little bit weirder, and it's going to lead to some weird consequences. That's why I'm trying to make you comfortable with that we need to use it. Okay? And now immediately, we can see how to generalize the notion of spatial velocity to 4 dimensions. We take dx mu d tau. Okay? And then coming back to the problem that we observed here, now Chase's answer would be correct in that what sits in the bottom of this is genuinely an invariant, it's a scalar. Okay? Because tau is defined in terms of ds squared, but ds squared is the same to all observers. In fact, that's kind of how we set up special relativity. It's that this thing appears to be to all observers. Dx mu is, of course, a vector. Dividing the vector by the scalar gives us a vector for the velocity. Okay? Okay, so I'm going to give you one more piece of language here. For an object at rest, the expression for ds squared, of course, simplifies because, as we talked about earlier, dx, dy, dz are 0 if you're at rest in a particular coordinate system, and so this just becomes minus c squared dt squared. And so this lets us identify tau, or d tau, if you will, to be, well, the magnitude of this is just c squared dt squared, and so when I take the square root of that, this is just going to be c dt. Okay. But this is the rest time. That is, this is the time measured in a reference frame where the object in question is at rest. Okay, so now I'm going to say something which is going to bother you and bothers most people. All right? The d tau is equal to c dt rest when I evaluate this in the rest frame of a particle. but the value of d tau is an invariant. So in any other frame, it has to have this same numerical value. So we can call d tau the rest time and use it even if we're in a different frame. That's what bothers people, okay? I will probably try and stay away from calling it rest time just because that makes you think, oh, I have to be working in the rest frame. All right, and I'll probably just refer to it as tau, or I'll try my best to just refer to it as tau, okay? But the idea, just to summarize one more time, d tau is an invariant. I can evaluate it in any frame and get a value, but that has to have the same value in any other frame because it's invariant, okay? All right. Let's see what we can get rid of here. Any questions before we? Yeah.
So the fact that you can kind of move the dt over to the other side makes sense when you get d tau over dt rest equals c. Is that kind of what tells you the speed of light?
So, well, sorry, the c. Okay. So the c. If I wanted to make this a quantity with the dimensions of time, okay, then I would define it with a c out front. And then I would identically say d tau is the rest time, okay? I'm being a little sloppy here because I'm literally thinking of tau as the length of the path. And the length of the path is measured in distance units.
Yeah.
Okay, so don't get too hung up on that factor of c there, because the next comment in my notes is that we're going to do the only sensible thing at this point in the course, and that's set c equal to 1. So it's going to disappear from all subsequent discussion. Yes?
So the entire basis of this argument is kind of based on the fact that the negative c squared dt dx squared dy squared plus dz squared
Yeah.
is invariant. Why does it have to be invariant? Because if you have like length contraction or whatever, won't dx, dy, and dz change with respect to your different reference frames?
Absolutely. Shit. I was hoping somebody wouldn't ask that. That was the one thing that I didn't know the answer to. No, I'm just kidding. No, yeah. So if you change reference frames, dx does change by a factor. dt changes by a factor, but the point of it is that all of those changes together, which you're thinking about relativity from the three-dimensional perspective, where you think of what's happening in the spatial directions, and then separately what's happening in time, and time dilates and length contracts. In four-dimensional space-time, where you think of all of these things happening at once, the whole point of it is that in 4 dimensions, this is the length of a four-dimensional vector. The length of the four-dimensional vector is invariant. The spatial parts might change size and the time part might change size, but the length of the thing in 4 dimensions remains constant. That's sort of the whole premise of special relativity. It's just when you go back to the three-dimensional language where you've learned it before, it doesn't really seem to jive.
Thanks.
So what are the units of u?
What are the units of u mu? They're the units of dx mu over the units of tau.
Yeah, that's kind of confusing because it's the derivative of time and then derivative of velocity.
I know. I'm gonna show you something way more confusing than that in just a minute. So with regards to units, because henceforth it's going to get really confusing until you get used to it. Henceforth we're going to set c equals to 1, okay? Which means that we're measuring distance in light seconds. Okay, so the speed of light is 1 light second per second. Okay, and essentially the factors of c pop up everywhere. People tend to keep c in the story in special relativity more often than in general relativity. C does play an important role in general relativity, but you can always, it gets way more clumsy to carry around the factors of c in general relativity than it is in special relativity. But you can always restore the factors of c you're asking exactly the question you're asking, which is, okay, do the units of the quantity that I'm writing down make sense? So, one classic place where we might encounter, do I need to put in a C, where does it go in? So when we have the gamma factors, which appear in time dilation and length contraction, in our new convention, they will be written like this. Well, this expression to any Physics 100 student clearly makes no sense, because 1 minus a velocity squared is just not, the dimensions are not making sense. And so how do you fix it? You divide by c squared, and that gets that thing to be dimensionless, and then subtracting it from 1 makes sense, okay? Or if I give you a mass, and you're expecting an energy, you just multiply by c squared. That's how Einstein came up with the formula. No, I'm just kidding. We are going to see where that formula comes from today, but that's not what it is. Okay, so at the end of the day, though, I will agree with you. The dimensions of this look weird, but let me point something out to you in just a minute, which is going to come back to exactly that. Okay, so going forward, I'm not going to have C's in places, so don't point out that I'm missing a C. We will mercilessly mock you for having fallen asleep during that critical part of the discussion. Okay, so this next topic is what I like to call mu weirdness. Because this thing's got some funny properties. Here's one of the weirdest properties. Let us calculate the speed squared, or the velocity squared, which is the same as the speed squared. Okay? So we know how to do this, all right? We take basically the 4-velocity vector. So by the way, if it wasn't obvious, this is what's called the 4-velocity. We take that vector, we form the dual vector, and then we contract the dual vector and the vector indices to create something that's invariant. Okay? So the way we would formally do that with the metric would look something like this. And you are all now experts in how that index notation expression works out. But now let's actually just put in our definition of the 4-velocity. So I'm literally going to write in these quantities. Okay? And now I'm going to play one of those fun games where I move all of this stuff up into what I might think of as a numerator, and then I'm going to put everything in the bottom in something I'll call the denominator, and then that of course just becomes d tau squared. Okay? Now d tau squared, remember, this is a quantity that I want to be positive, because d tau would in principle be the square root of that. So that means that d tau squared for something which is moving less than the speed of light has to be minus ds squared. Because remember, we pointed out that if you're moving less than the speed of light, ds squared itself is negative. And so for this root to make sense, we have to put a minus in front of it in order for that square root to not be imaginary. But that means that in this expression, I can write, instead of d tau squared in the denominator, I can just write minus ds squared. Okay? But it gets gooder, because minus ds squared can also be written as minus a to mu nu dx nu dx mu. I mean, that's what ds squared is. It's dx lower mu dx upper mu. This is going to be a hard one. Chasen! Where are you, Chasen? Chasen! What's that equal to?
Is it just one? Wait, no. -1?
Yeah, it's -1. I mean, it's so crazy, like, I'd be scared to say it. It's -1. Now, if you think about it, that's weird. If we take the 3 velocity of something, vi, and we square it, so we're trying to do v dot v, which would be vi, okay? Then this is the speed squared. You know, that's something we learned in Physics 1. So the square of the velocity in 3 dimensions is the speed squared. But it depends on how fast you're going. What I just proved to you is that the 4 velocity squared is equal to -1, and I never even told you how fast you were going. In fact, you get -1 no matter how fast you're going.
Unless you're going to speed of light. Does the speed of light?
Okay, so Adria actually, she actually reminded me of a very, very interesting point that I need to make, and that is that this definition with this parameterization breaks for something moving at the speed of light. Why does this break for something moving at the speed of light? Well, I mean, I know what you mean when you say that word, but I don't think, anyway. Why does this parameterization break? What is the size of ds squared for something that's moving at the speed of light? It's 0. I mean, let's just look at it. If you're moving at the speed of light in the x direction, then dx dt equals c. Okay? That means that, of course, dx is c dt. And so if you're only moving in the x direction, dy dz is 0, and so this is plus dx squared, but that's c squared dt squared, which is 0. Okay. So I haven't said it before, but, and it's because it's so second nature after you've done this a while that you forget to point it out. The defining feature of light in this story is that light travels along paths of 0 length. It doesn't go anywhere.
Right, that makes sense.
Yeah, I know. These are called null paths. They are paths which in space have a length. I mean, light will travel a spatial distance, but in space-time, they have 0 length. And there's a lot of really, really interesting stuff you can do with that idea, okay? But it is unique to things which are massless. It doesn't necessarily have to be light. It's any massless thing. Travels along these paths where ds squared is always 0, identically. Okay? But that being said, if ds squared is always 0, then taking the square root of it is not really going to provide us with a good parameter. Okay? So we instead use what's called an affine parameterization. We're not going to need to go into that at any point in this course, actually. But there is a way to define a consistent 4 velocity for light. I'm going to show you some expressions a little later on which actually generalize to the case of light, even though we don't at this point have a consistent way to parameterize the path of light. All right, where was I? Yes, okay, so what I want to do now is I want to give you some reconciliation with this oddball fact. Okay. Does everyone understand why this is odd? Like, right, in 3 dimensions, if I square the velocity, I get the speed squared, and this is something which changes depending on how fast it's going. But in 4 dimensions, with the definition I've given you for the 4 velocity, when you square it, you always get -1, and that might bother you. Like, it doesn't depend on how fast you're going. Okay? But the thing to remember is that we're not parameterizing things with time. We're parameterizing things by the actual distance they've traveled. So let's try to do that same thing in 3 dimensions. So if I define the velocity, and I'm putting this in parentheses, this is where it would be awesome if a Phys 1 student turned on the lecture on YouTube and like started watching this. That's velocity? Really? Okay. But that's why it's in quotes, because it's not really velocity. But if we tried, then we might say, okay, the velocity has components dx, dy, dz, and I'm going to take the derivative with respect to the distance traveled. So that would just be something I might call ds. That's the spatial distance that you traveled. Okay? So ds is the path length. All right. Well, now, of course, if we take two of these and dot them together, then we're just going to get dx squared, ds squared, plus dy squared, ds squared, plus dz squared, ds squared, which is, of course, going to be 1. Because dx squared plus dy squared plus dz squared is ds squared. Okay? So the fact that we're getting a fixed value for the square of the 4 velocity is just tied to the fact that it's being defined with respect to the distance traveled. If you travel faster, you'll travel a larger distance. So both the numerator and the denominator in that definition get bigger together. Okay? Okay, so as unsettling as it is, this is a very important result to write down because we'll use it at various places. U mu equals -1. And now what I want to do is start digging into exactly what this u mu is, which is going to entail some more u mu weirdness, but we really need to get something on the table because dx nu d tau is just, it's not got a lot of meaning to us. So let us investigate now the components of the 4 velocity. And what are the 4 components of the 4 velocity? So in order to make sense of this, we're going to have to set up some frames. So the components of the 4 velocity are going to be the components as seen in a frame S where I'm using the coordinates t, x, y, and z. So remember, this is a vector in space-time, so it transforms between different frames. So when I say I'm going to write down this vector, I need to tell you what frame I'm writing it down in. So I'm going to write it down in the frame S, that uses coordinates t, x, y, z. You'll notice the conspicuous absence of c, because c is now equal to 1. Thank God. Right? So the frame S, and then what I'm going to consider is a second frame, which is the frame. Now, I'm talking about the components of 4 velocity. So I want to, like, if I'm thinking about 4 velocity, I'm looking at an object and it's moving. Okay? So I want to talk about the 4 velocity of that object that's moving. So I can think of it like a point particle, that's fine. So there is a special frame associated with that particle, and it is the frame in which the particle is at rest. So we call that the rest frame for the object. And we can place the object anywhere we want. We might as well place it at the origin for simplicity. But the idea is that as the particle moves, this frame moves with it. But we're in this frame, and we just want to describe what we're seeing. Okay? So the 4 velocity that I'm trying to describe in the frame S is the 4 velocity describing this particle. Okay? So here we go. There is, of course, first off, the time-like component, which by our definition would just be dx0 d tau. Okay? But dx0 is just dt. Remember, we've set c equal to 1. dx0 used to be c dt, but now it's just dt. Okay? And now I want to pay attention. D tau is an invariant. dt changes between different frames. Okay? In particular, this is the dt in this frame, in the frame S. It's an unprimed dt, or it's I should say, I'll refer to these things as rest quantities. So I'm looking at the dt in this frame. But I know how the dt in this frame is related to the dt in this frame. It's related by a factor of, we wish, gamma. Okay, so this is time dilation. So think of a clock at rest in this frame ticking, and then I want to know what is the length of the ticks as seen in my frame, where I'm watching the clock tick.
So, we're talking from the rest frame to the non-rest frame.
Yeah, well, dt is the time interval seen in the S frame. Okay? So just going straight back to your time dilation formula, this is gamma dt rest. Okay? If you see a moving clock, the ticks are slower by a factor of gamma, or the time intervals are longer by a factor of gamma. Remember, gamma is greater than 1. Greater than X. Okay? We all good? Yeah. We all good? Okay, ready?
Wait,
Yep.
gamma does have to be greater than 1 in this case, because otherwise the dt falls apart, yes.
Yeah, sure, yeah. If it was, it's only equal to 1 if you're in the rest frame. Right. Okay, yes.
Was the rest frame not defined as everything equaling 0? So would dt in the rest frame, we're not defining
No.
it as
So
0,
we're thinking,
it's defined as space at rest.
For this object, when you're at rest, so I'm at rest. See me. I'm at watch Alex go in time. Because even if I'm at rest, I'm not at rest in time.
Okay.
Like I still propagate into the future, even though my dx, dy, dz are 0. Okay? Write a kid's book. Watch Alex go forward in time. Okay, here we go though. Here is where I'm going to come back to that weird thing that I told you wouldn't like. All right? dt rest is exactly d tau. Remember, c is equal to 1. So this is just gamma. Okay. So the 0th component of the 4 velocity, remember that was the first thing I said. What is the 0th component of the 4 velocity going to be? It's just going to be gamma. Okay. To figure out the rest of the components, because we obviously can just do one of the spatial components and then the answer will generalize, we play another one of these fun games. dxi d tau. That's the definition of that component of the 4 velocity. All right? But now let's just be sneaky. And break that up into dxi dt dt d tau. Where time is the time in the frame S. Where I'm also measuring the coordinate xi. So xi and t live in the same frame. Well, in the frame S, where you use coordinates xi and t, what is the quantity dxi dt? It's the velocity, the 3 velocity. Or it's the ith component of the 3 velocity. So this is just vi. Benjamin, what's dt d tau?
It's d gamma t rest, or gamma dt rest over d tau,
Which is
just gamma.
just gamma. So this is gamma. Okay. So at the end of the day, what we find is that the components of the 4 velocity are just gamma, and then gamma times the components of the 3 velocity. Okay? I know. It's pretty sweet. Now, one very important thing that if I don't point it out might not be obvious, but I got the stuff on the board to say this. There's obviously a v right there, okay? And that's the velocity of the particle. there's also a speed in here. What speed goes in here?
The V in the moving frame. Or seen it from the moving, or with respect to the moving frame.
The V of the moving frame.
The V of the frame. So remember, the gamma factors tell us how this frame is moving with respect to this frame. Okay? So that is subtle because the V is the velocity that this person sees the particle move with, but the V that appears in gamma is the velocity that this frame is moving with respect to this frame. So you've got two different V's in this expression. Not! They're the same V. This frame is defined as the frame where the particle is at rest. So whatever the particle is doing, the frame's doing it. So the velocity of this particle is the velocity of that frame. So the good news is this V and the V that you stick into the gamma factors, they're all the same V's. Okay? It's not obvious. One is the V of a particle, one's the V of a frame. But since this particle is tied to this frame as its rest frame, then they're the same V's.
And that will always be the case.
That will always be the case. Yes, ma'am. Okay, so let's just do a quick check to make sure that this isn't bullshit. Let's calculate u mu u mu. What should it be? -1. Damn straight. Let's check it out. We've got this thing, u mu. What is u lower mu? Somebody yell it out. It is. It absolutely is. Thank you for that. What are the components of u lower mu?
Negative gamma V.
Yeah, exactly. They're negative gamma V, because as we've learned, and hopefully from your homework you've seen this, when you take a vector and you want to find the components of the dual vector, you just switch the sign of the first term. Okay? And I'll write, you don't have to do this with matrix multiplication, but I know you all love matrix multiplication. So if you want to multiply these two things together, there you go. What do you get? You get minus gamma squared plus gamma squared V squared. And you can plug in your expression for gamma, and you'll find that that is in fact -1. Okay? Let's get a victim. Mike! I know, you gotta wake up now, man. Ready? Here we go. We got one last observation before we move on. Remember, this is our definition of the four velocity. One last important observation. What are the components of the four velocity if you are in the rest frame of the object?
And it should just be. Gamma and 0.
So gamma and 0, but what is gamma if you're in the rest frame of the object? Yeah. that was the What else can it be? It's 1, 0. Okay. So the four velocity actually takes a remarkably simple form if you're in the rest frame of something. But it's interesting. Notice, as I promised you, something at rest still has a non-zero four velocity because it's still moving through space-time. It's moving through time. Okay? And hopefully you can do this in like 3 seconds in your head. U mu in the rest frame is -1. Okay? It's always -1. We can change frames at will and it will still be -1. Yeah, Alex?
Is that expression still the case in the accelerating frame?
No. No. And accelerating frames in this class, you can certainly write down what things look like in accelerating frames. You're not going to get a lot out of it. And we should be careful because we should be careful about our description of an object which is accelerating. I know that we described the velocity of an object in terms of a transition between frames. And you could so too think about an object at rest in a frame, and then if that object is accelerating with respect to me, then that frame is accelerating with respect to me. But if you want to connect frames that are mutually accelerating, then you can't do that with Lorentz transformations. It kind of takes you outside of the standard set of transformations that we work with. But you can do it in special relativity. You can describe accelerating things in special relativity. That's a classic misconception that special relativity can't describe acceleration. It certainly can. Okay, but the expressions are definitely going to be different. Everything is nice and clean as long as we're connecting inertial frames to inertial frames. The moment you start getting away from inertial frames, things get ugly. Okay, so in the last 2 minutes, let's do dynamics. Because we got time. We got 10. All right. Fortunately, dynamics now follows from everything that we've done, because after all, the key part of dynamics that we want to talk about is momentum, and in particular, how do we define momentum and how does momentum appear? Now, it turns out that for what we're going to do in this class, Newton's second law is not going to cut it. Sorry. So I'm not going to worry about summing forces and talking about accelerations and talking about derivatives of momentum. I'm just for now going to talk about momentum itself. And then our next topic is actually going to start turning to how do we actually fill out the story of dynamics. It's just, we don't even use an analogy of Newton's second law in this class in the way that we use 4 velocity instead of 3 velocity. But we do use momentum, so let me go ahead and talk about momentum. Clearly, we want to replace this with something that is a 4 vector. The most natural guess, which actually turns out to be the right guess, is to multiply the 4 velocity times the mass, okay, of the object which is moving. Now, depending on who taught you special relativity, you might or might not have heard of the idea of relativistic mass. You might have some idea in your head that m changes depending on the observer. Forget that. That's not what's going to happen in this class. M is the mass of an object, period. It doesn't change. You can call it the rest mass if you want. I'm not going to call it the rest mass because it's the only mass there is. It's the mass. Okay? Of course, we can immediately write down the components of the 4 momentum because we know the components of the 4 velocity. So in any reference frame, the 4 momentum takes this form. And from this, we get a whole lot of love. For example, if we have something which is moving much, much slower than 1, remember 1 is a proxy for c squared. Okay, if we're in the non-relativistic limit, I know, it's weird. 1 is a big number. 1 is the, okay. Then gamma, the gamma factor, okay, we can expand and approximate by 1 plus 1/2 v squared. Okay, and there are higher order corrections to this. Okay? But if we do that, then P mu takes the following form. The time-like piece, m gamma, becomes m plus 1/2 m v squared plus higher order terms. And then m gamma vi, okay, the ith component of the velocity times m times gamma, becomes m vi plus terms of order vi, or high order terms, say higher order terms. Okay? And now we recognize the deep and weird problem that confronted Einstein. Because in expanding this definition of momentum for slowly moving things, we of course discover the usual definition of spatial momentum. Okay, so this would be your non-relativistic momentum. And then there are relativistic corrections to that. But the leading order term is the non-relativistic momentum. That's what you would expect. That should be the dominant answer if you're moving slowly. Okay? This one is weird. Because for this one, we see a term which classically we can interpret. What is that? That's the classic non-relativistic kinetic energy. What else could it be? But where it gets weird is that there is a term that is even more important. What is this term?
A mass.
It is a mass.
It's E over C squared.
Well, if we lost our factors of c because we set them equal to 1. This is secretly mc squared. Okay? This is, of course, what we call the rest mass term. And what's interesting is that it's there even in the non-relativistic limit. Okay, things have a rest energy even in the non-relativistic limit. Okay? Now, to make the language even weirder, if this is kinetic energy, then obviously this top piece, the time-like piece of the form momentum, has something to do with energy. So, for lack of a better name, we're going to call this the relativistic energy of the object in question. And then we're going to call this the relativistic momentum of the object in question. Okay? The relativistic, because it includes all of the corrections. In fact, you can write E relativistic as just m gamma, and you don't have to even make an approximation. The relativistic spatial momentum, this is like 3 momentum, okay? You can write as mvi plus the corrections, or you can just write it as m gamma vi, all right? You've got to be careful because there's the spatial momentum, but the spatial momentum combined with the energy are the components of the 4 momentum in space-time. Okay. This is why it's important to distinguish. Mu is always a space-time index. I, whenever it appears, is a spatial index. Okay? Okay, so if we just come back very quickly, so we can write that the components of the form momentum are the relativistic energy and the relativistic spatial momentum. Then we know that if we take p mu, this is just going to be m squared u mu. So what's that going to be equal to? Negative m squared, right? Because u mu. U mu is always equal to -1. Okay? This is an invariant. It's the square of, it's a vector contracted with a dual vector. So in any frame, the numerical value of this has to be -m squared. Okay? But we can ask, what does the expression look like in a frame where, you know, for example, you see E relativistic and P relativistic, and in that frame, you would get exactly minus E relativistic squared plus P relativistic squared. Okay? I'm just squaring, I'm taking this vector, I'm making the dual vector by making this term minus, and then I'm contracting the two. Yes, ma'am?
Should we just like give up on unit analysis forever?
I'm going to restore the C's in just a
Okay.
second. Okay? So putting back the C's, and then doing a little bit of rearranging here, this expression becomes E squared equals p squared c squared plus m squared c to the fourth. Okay. Which is just the relativistic mass-energy relation. Mass-energy momentum relation. Okay? All right, so the last thing I'll point out is just a piece of notation, just to kind of connect this to things that you've heard before. We can take p mu, and we can actually classify it according to the values of m squared. So if m squared is positive, what's the sign of p mu? So p mu is minus m squared. If m squared is positive, what is the sign of p mu? It's not a trick question. It's negative. Okay? What about when m squared is 0? It's 0. What about when m squared is less than 0? It's positive. Okay.
When are you ever going to have like a mass that's less than 0?
Mass squared less than 0. A mass less than 0, like you might could wrap your head around. So this is what's called a tachyonic state. Classically, people think of it as something moving faster than the speed of light. That's actually a misconception, and if you want to read more about that, go read my thesis.
That's to be light reading.
In fact, literally the first few pages are explaining the difference between the true tachyons we encounter in physics and the ones that people think of as moving faster than the speed of light. But the important observation is that whenever something is massive, which is the things we really are describing, you should always expect their form momentum to square to something less than 0. But of course, if something is moving at the speed of light, other massless particles, then the square of the form momentum should be exactly 0. Things that are moving less than the speed of light, we call time-like. We call it time-like because it's moving more in the time direction than in the spatial directions. For example, if you're at rest, you're only moving in the time direction. So generally speaking, something moving subluminally, lower in the speed of light, we call time-like. This we obviously call light-like, and this we call space-like. So when I refer to a time-like momentum, I'm just saying it's the momentum of an actual massive object. And you know the square of it is less than 1. And likewise for light-like and space-like. All right, that's it for today. We'll come back tomorrow. We'll talk about the sexy topic of densities. I mean Thursday. You knew what I meant. Don't give me grief.
How is your items that have been dropped? How's that going?
Yeah.